And this is my Physics 2211 Lab 2 on motion of a falling object. So the purpose of this lab is to observe the effects of drag on an object in free fall and to simulate those same effects, and to compare models computed with and without drag to those real-world results. The aim is to show that there is a force of drag counteracting that of gravity. So a few of the formulas and concepts that will be used in this lab. First of all, we have Newton's second law, force equals mass times acceleration. In this lab, that'll be used with negative g, the force or the acceleration due to gravity, which is 9.8 meters per second. That will be used as the acceleration. The force of drag, we're going to use a simplified version of that formula, where b is a constant that includes the drag coefficient cross-sectional area of the object and the density of the fluid the object is falling in, which in this case is air. And then we will also be using the velocity update and position update formulas, and those are going to be in the simulation, and those are both also derived from Newton's second law. So the procedure for this lab is to take a video of the motion of a falling object with non-zero drag. We're going to use Tracker to analyze the video and construct a position versus time graph for the object, and then construct a computational model with and without drag as a factor of the motion of the falling object. And we're going to create a graph containing the real-world results of both models and compare and compare the real-world results to the results from the simulated models. So for the motion of a real-world falling object, I used a piece of crumpled up paper, which was the system in this case, and the air around it, and the surroundings included the ruler used for measurement and me. The object was dropped with as few external forces as possible, although some could still be at play, including maybe some spin or force from my hand on the piece on the paper, and potential drafts in the room. So using Tracker, we could see that the piece of crumpled paper dropped 0.86 meters, and its initial velocity was theoretically 0, although there's some chance I could have put some force on the ball when or on the piece of paper when I dropped it, and the motion accelerated at slightly less than 9.8 meters per second, which can be seen in the position versus time graph above. So the main edits for the computer model of the falling object, I used GlowScript, and the main edits I made to that formula included to the starter code for that included changing the formula for force to account for both gravity and drag. So the gravity was using Newton's second law, where the mass of the ball times negative g was the force of gravity, and the force of drag was given by b, which is the constant including several factors, times the square of the speed of the ball, or the magnitude of the speed of the ball and the magnitude of the velocity. And the position and velocity update formulas were also used down in lines 77 and 79 to show the how the ball to update the position of the ball throughout the simulation. So this is the final graph that I created using Google Sheets, which shows the observed experiment in blue, the simulation without drag in red, and the simulation with drag in yellow. As you can see, they both started off pretty close to both simulations started off pretty close to the observed acceleration, but the model without drag eventually tapers off, whereas the model with drag stays very accurate to the curve, which shows that there is definitely drag at play in the case of the real-world experiment. So what does it mean? Do any of the models predict a terminal velocity? Not within the given time frame of the experiment, but the model including drag would predict a terminal velocity past a certain point, as the squared speed in its formula would eventually make the force of drag surpass the force of gravity. Would throwing the object down change its terminal velocity? It would not, as no part of the drag or gravity equations would change as a result of it. And it would be the equivalent of starting the same velocity with respect to time function, just in a certain amount of time down through that function.